Hi guys, in this video we're going to continue our discussion of systems of linear equations in two variables and how to necessarily find solutions to a system of linear equations in two variables. And that method that we've discussed so far is finding solutions graphically, okay? Which means what we're going to do is we're simply going to graph both the equations in our system. Since each equation makes its own graph of all of its own solutions, what we're looking for is a solution that makes both equations true at the same time. In other words, we're looking for any points where our graphs would collide, because that would be a point that would make both equations true simultaneously. So let's go ahead and get on with this. Yes. Let's go ahead and take a look at system number 1 up here. We say 2x minus 2y equals negative 8 is our first equation. 2x plus 2y equals negative 4 is our second equation. I'm going to go ahead and start by graphing these. We're going to use the intercept method for graphing these. And honestly, let's do this. Let's make this set of axes in blue as well. That way we have consistency. We say, okay, so let's go ahead and find the intercepts of our first graph, because it's in standard form. It's easy to graph it using the intercept method. So if we plugged in, say, 0 for y to find where it hits our x-axis, we'd say this would go away, because anything times 0 is 0. We get 2x equals negative 8. So solving for x, dividing by 2, we get x is negative 4. Okay? So when y is 0, we get x is negative 4. 1, 2, 3, 4. Okay, so it hit our x-axis at negative 4. If we set now x equal to 0 and solve for y, we get negative 2y equals negative 8. Therefore, y must have been 4. Okay, so we'll go up 4 on our y-axis. 1, 2, 3, 4. And we say, all right, there's our y-intercept on this graph. Let's go ahead and draw in all of the solutions to this graph, which fall in this line. And we should label this. We should call this equation 1. That way we don't mix up which line was which equation. Now our second equation here, if we plugged in 0 for y, that would go away. We get 2x equals negative 4. Therefore, dividing by 2, we get x is negative 2 when y is 0. So we say negative 2 on our x-axis is where it hits our x-axis. And if we plug in now 0 for x, trying to find our y-intercept now, our y-intercept is also at negative 2 if we divide by 2 there. So we'll go down 2 on our y-axis, draw our y-intercept, and then sketch in all of the solutions to this graph. Okay, all the solutions to this graph are on this line. And now you've got to realize something here. First things first, that I've drawn this by hand. And drawing it by hand is not very accurate. I should be using graph paper and a straight edge to be very, very precise. Okay. The second thing is this. We're looking for a solution that both of these equations had in common. We're looking for a solution to the entire system, a point xy that would make both equations true simultaneously. And that point would have to be where our graphs intersect, if they intersect at all, which looks like, this point right here. Now, if I had to guess, this looks to me to be the point. If there's negative 1, negative 2, this is like negative 3, comma, maybe up 1 in the air. Okay? So if I suspect that negative 3, comma 1 is a solution, I'll put a big fat question mark over it. We have to check this. We have to plug it back into both equations to see if it satisfies them both. Let's go ahead and do that now. We say 2 times x minus 2 times y equals negative 8. If I plug in now negative 3 and a positive 1, we get negative 6 minus 2 is negative 8 in our first equation. So negative 8 equals negative 8. So this works. We can put a check mark here. Show this is a valid solution to the first equation. It works in that. We now need to check the second equation. So we'd say, okay, so 2 times x plus 2 times y is negative 4. We'll plug in negative 3 for our x and 1 for our y. We get this, negative 6 plus 2 is negative 4. We get negative 4 equals negative 4. So this is indeed, just by drawing this by hand, we were able to determine that the point negative 3, comma 1 was the common solution for both systems. But the important thing to note here is it's where their graphs intersect. Okay? And just to really kind of strengthen our argument on this one, we'll go ahead and graph the system that we had here. We said 2x minus 2y equal to negative 8 was our first line. There she is. And we said our second line was 2x plus 2y equal to, I think it was what, 4 or negative 4? 4. Okay, there's our second line. Let's make sure I get this right here. Oh, I said negative 4. I apologize. Let's go back over here. This was this was 2x plus 2y equal to -4. And you can see that most definitely the point -3, 1 was a solution to this system, but it was where the graphs intersected. That's what we want. Okay, this method of solving by graphing. Okay, so now let's go take a look at our second system over here. Our second system, Roman numeral II. We're going to do this again with the graphing method. So if we want to find a solution to a system, one very good way to do it is to go ahead and just graph both equations and see where they intersect. So we say, okay, let's go ahead and get on with this. We say, all right, they're both in standard. Let's graph using the intercept method. So we say, what if we plugged in 0 for y in our first equation? We would get 3x equals 6. Therefore, x is 2. Okay? So we'd say, hits our x-axis at 1, 2. There's our x-intercept. Let's find our y-intercept now. Plug in 0 for x, and we get -2y equals +6. Therefore, y was -3. So it hits our y-axis down 3. There that is. Here are all the solutions to our first equation. They're all on this line. We need to label this EQ1. So now graphing our second equation, we see this. We say if we plug in 0 for y to find where it hits our x-axis, we get 6x equals 12. So x is 2 when y is 0. So we'd go over 2, and you'll notice that it has the same exact x-intercept. So we just go ahead and draw overlapping that one. We say, all right, so plug in 0 for x now and solve for y. So -4y equals 12. Therefore, y would be -3 when we divide both sides by -4, but y would be -3 when x is 0. So that means on our y-axis, I'd go down 3 and draw a dot. What you're going to notice is this second equation is pretty much right on top of the first equation. So what we mentioned is this. Well, hold on a second here. If we're looking for all of the points that satisfy both equations, then we're looking for all of the points that both graphs have in common. And in this case, the second graph lies right on top of the first graph. So not only do they run into each other, they run into each other at infinitely many points. So when we consider a system such as this one, what we'd say is this has infinitely many solutions. Infinitely many solutions. Not just one time do they run into each other, but they run into each other indefinitely. Okay? And you might notice this. As a matter of fact, the second equation here, if you were to take the entire first equation times 2 throughout the whole thing, you would get the second equation. So they really are the same equation if you think about it. But this would be a case where we have infinitely many solutions. Cool. Okay? Let's go ahead and take a look at system number 3 up here. We say we want to solve this by graphing, so we're going to graph both of these and find out, well, what are the points that both equations have in common? What are the solution points that they both have? Where do they run into each other, essentially? So we say, okay, so 3x minus 2y equals 6. We'll start by graphing it. If we plug in 0 for y to find where it hits our x, 3x equal to 6, then it must hit our x-axis at 2. So we'll go over here, 2, draw on our dot. Let's find our y-intercept now by plugging in 0 for x. If -2y equals 6, then y equals -3 is where it hits our y-axis. So we'll go down 3 on our y-axis, draw on a dot. So here's the equation, the graph of the equation of our first line. Not bad by drawing this by hand. This is EQ1. These are all of its solutions. Now if we graph the second equation and plug in 0 for y, we get 3x equals 2, so x is 2/3. Okay, so it hits our x-axis at 2/3. Be about, about right there. And then if we plug in 0 for x, y would be, well, y would be -1. Okay, so we go down to -1, draw a dot, and sketch this in. What I want everybody to see, though, is essentially this. These lines would never hit. These lines are actually parallel. Whoops, equation 2. So if these are all the solutions to the first equation up here, and these are all the solutions to the second equation, the question is, would there be a common solution? Would there ever be a solution that they both had at the same time? And the answer to that is just simply no. There are no common solutions ever because they never overlap. So we'd say this one has simply no solutions. Okay. So here's what I'd like to do. I mean, because I know maybe somebody's watching this taking notes. There are 3 types of systems that we have, and we want to sketch all of them. But we'd say, okay, so here's system 1, system 2, system 3. And whenever you solve systems of linear equations, it has to come out to be one of these 3 situations. The first one is this. Maybe your first equation does this, and your second equation does this, and we say, do they have a common solution? And we'd say, yes, where they intersect, there would be one solution. One and only one solution. So this is the one solution case. The one solution would be at x comma y, where they overlap. And we say that this system has a name. We say it is consistent. Why? Because it came out to have an answer. We say consistent independent. How am I supposed to remember that? I always think of it this way. It's consistent because it has a solution. That means it has a solution. And they're independent because these lines don't depend upon each other. They do their own things. They do different stuff. They do their own thing. The second scenario is this, where we have one line and we graphed it, and we said now we have another line. I'll try to make this look like they're overlapping here. And these lines were right on top of each other. So we said this had infinitely many solutions. Infinitely, that's an N. Many solutions, okay? And this type of system has a name also. Since it had at least a solution, we would refer to this one as consistent, because it had at least a solution, consistent, but we say this is the consistent dependent case. They're dependent because these lines, one depends upon the other one. They live together kind of thing. They're on top of each other. And we say, all right, the last possible case was the case where we had two lines that were parallel. Let's scribble this one down. And I know that's very, very ugly right there, but we'd say this has no solutions. No solutions, okay? And we would call this inconsistent. Why? Because it didn't even have a solution. And by the way, if you're taking notes, you want to write this was the case where the lines are parallel, okay? So when we solve systems, this bottom right corner is very important because you're always going to get one of these three things. Either there was one solution where these lines intersected. There are infinitely many solutions if they are the same line and they're right on top of each other because they share all of their points, or they never share a point because they were parallel. They never ran into each other. And those are the three types of possible outcomes to a solution to a system of equations.